Okay, let's get started. Welcome back to our software testing and the quality assurance class. Okay, in today's class, we will finish our kind of big survey about all the quality assurance activities and the techniques. And by the end of today's class, you should be able to start really thinking carefully about your course project for the semester. Okay, and so I will be spending some time towards the end of today's class talking about the project, and particularly the project proposal will be due in about 2 weeks. Okay, and I have also posted the first homework assignment, which will be due Monday, next Monday. Okay, so it's a kind of you'll have first have the homework assignment, and then you have the project proposal. So those are the two things on your part you should be responsible for. Okay, of course, for the previous two classes, I didn't give you a specific assignment, but you were supposed to follow their course contents and the material and read the things yourself. Okay. Before I continue with the class material, are there any questions so far? Okay, and I'll talk a little bit about the homework towards the end of today's class also. Okay, so homework assignment number 1, kind of I'll talk about homework and project together. Okay, so let me switch over to the computer now and bring up our class. Okay, so in the last class, we started talking about some definition about our definition about quality, and then we really linked the quality to the high quality as equivalent to no defect or low number of defects or low defect impact kind of things. So because we are trying to establish this kind of link, we are viewing quality as kind of negatively correlated with defect. So what, in this kind of view, what we do about quality will be kind of like what we do about defect. Okay, so we had this picture about errors, faults, and failures, and then in terms of this defect, in terms of errors, faults, and failures, if we want to do something about the defect in terms of try to affect the quality, we will be dealing with either the errors, with the faults, or with the failures. Okay, so we start by looking at the different strategies of doing things. We kind of spend quite a bit of time on the defect prevention process improvement front. Okay, so essentially what you are trying to do there is to establish the first line of defense so that you will not inject faults into the system. Okay, so there are two generic ways of doing that. One way of doing that is to prevent the fault injection by direct intervention. Because the fault injection is because of errors. Errors are the missing or incorrect actions, human actions, missing or incorrect human actions that lead to the injection of fault into the system. So we can do something about the actions. Okay, so for example, we mentioned about some technologies or tools that can help us automatically block some of those actions or correct those actions. Okay, and then another way of doing that is instead of looking at the actions itself, but looking at the sources, the reasons for those actions, or we look at the error sources. Okay, so when we look at the error sources, you may have a misunderstanding about things. You have the chaotic process. You have some other reasons behind it. And then we can work on those reasons and do our process improvement or do our defect prevention. Okay, so that's the first line of defense we kind of talked about here. So this one bounced off and got removed. It's kind of like what we have the so-called error blocking. And then we have the direct error source removal. That's the two generic ways. Okay, and then we talked about well, if you have already some of the had some of the defects already in the system, the faults in the system, what do? Then you say, okay, I do a prevention. It's too late. Okay, no matter how good a job you do with the prevention, you will have some defect in the system. You will have some faults in the system. Okay, that's a given. Okay, that's a basically assumption. That's the reality. Okay, with the software systems getting so big, so complex, there's no way. No matter what you do, there will be some defects in the system. Okay, so what do you do with that? Okay, then what you do is that well, if it's in the system, can I try to remove them? Okay. Of course, if you want to try to remove them, you need to try to know where they are. Okay, and we mentioned about some of the kind of targeted and some of the not so targeted. So for example, that you can say, oh, this product is too buggy. I threw it away completely. Okay, but by throwing it away completely, I removed all the defects it had. Okay, so I say, okay, I can start from scratch and try to do a better job. And then the next time when I do it, because I have a better technology, maybe I have better people, okay, and a better process, and I have a better planning, and maybe I will produce a product that with only half about as many defects as I had in the first place. So that, if you have that luxury, that sometimes that's what you need to do. Okay, and we mentioned about the overall kind of expectations in software evolution is that you will go through change, and eventually some of the software will be kind of become somewhat change resistant. And no matter how hard you do it, well, not getting any much better. So at that point, you probably, the best option is to throw it away and move on to a complete new clean slate and then start from scratch there. Okay, but then assuming that you cannot do that, then you say, okay, I still have to work with this product. Okay, I cannot just throw it away. Maybe I can throw away a couple of small pieces, but not the whole thing. Then what do? Is that you cannot say, okay, this is what it is. I can do nothing. Well, you can do something. So you try to detect the underlying faults and try to remove them. Okay, so towards the end of last week's class, we kind of started to talking about various different ways of doing testing, and actually we went beyond chapter 3 a little bit and actually touched upon some of the things in chapter 6 and 7. So the overview about testing and the testing, the different testing activities. And although we didn't really using the slides from the chapter 6 or chapter 7, okay. And so that's one way of doing that. And in this picture is essentially this thing. You execute the software, running the software, you will observe some failures, actual failures, or some failures that you can see that if I don't remove it, I will see some failures during the testing. Not the field failures yet, but failures during testing. I go back, find out what caused this failure, and remove it, and I retest it. Okay, so this is a kind of simplified version, but the real process will involve doing this through some kind of iterative process. Test, locate the defect, fix, retest, and then maybe sometimes you go through that a couple of times before the problem got finally fixed. And then we looked at the different ways of doing testing, looking at the different kind of models for testing, different objects for testing, different objectives of testing, when do you stop testing, and perspectives of testing, all those things that give us those different kind of testing techniques, okay, and the different testing subphases that we fit into the development, okay. So that's kind of a very brief overview of testing we talked about in the last class, okay. And then when you look at the defect removal, detection and removal, we looked at the throw away the whole thing. We looked at the testing. And then there is another way of doing that that's very commonly used in software development organizations. It's through some kind of checking or self-examination. Okay, so in the software engineering community, we'll call this kind of somewhat more formalized review, examination, checking as the inspection. Okay, so this is what we are going to talk about a little bit. Okay, so inspection. Essentially, it ranges from very informal review to some of the very formal inspections. Okay, so essentially, what we are trying to do here is that, well, if you have a software product, okay, whatever things that is tangible, we will be able to examine. Okay, we will be able to examine it, and we will be able to try to find some problems. Okay, so you can print out some of the design document, some of the code, and or you can do it online, and you can look at even inspect the test cases. Okay, inspect the inspection process itself. Okay, so anything that is tangible, you can inspect. Okay, so any of those things. So we have the artifact from code, design, and test cases, whatever kind of things in the requirement phase, design phase, coding phase, testing phase, whatever kind of phase. So anything tangible from your software development process, you can inspect. So that is actually one of the key advantages of inspection. Okay, because when you do testing, testing is an execution-based activity. You must be able to execute something. Okay, so if you don't have anything executable, you cannot really do testing. Okay, you say, oh, what about you mentioned about I have some design, I can simulate the design, and then I can really test it. Well, in that case, is that you have some tool to make the design executable. Okay, so you can simulate it. What if I use this design, what will be the end product? So you make something kind of executable. So you have to wait for something to be executable before you can do testing. So that's one of the key limitations there. And actually, when people look at testing versus other quality assurance activities and other things, that's one of the key drawbacks with testing, is that you have to wait until some later stage before you can do testing. Okay, and so that's one of the key things is that people say, okay, you can do this and do that, and then instead of testing. And of course, it's like a defect prevention. We say, okay, we try to do a good job in defect prevention, but we cannot guarantee it will be completely defect-free. So we can do other things, but we still will be testing the system. Okay, no testing of the system is just not an option for any larger systems, because we all had the experience that without testing it will not work. Okay, doesn't matter it's Obamacare or whether it's whatever the website for the Obamacare or whatever things. If you don't do testing, if you don't do adequate testing, it will not work. But before you can do testing, you can do some inspection. Okay, so for example, that we all had some experience with some kind of informal reviews, even with that doesn't matter what kind of background that you have, even if you don't have any working experience. Well, you are in this class. Presumably, you have written some programs before. You had some basic exposure to software engineering and some basic exposure to computer science and programming. If you did programming before, if you wrote a program before, well, you have to look at your program. Okay, and that is actually one of the things. This is related to some of the computer science, software engineering education. People say, okay, what kind of language do you know? Okay, you know English, you know Chinese, you know French or whatever kind of language. How do you learn those languages? First, you learn by listening to other people, by sampling, you learn to read first before you learn to write. Okay, and then some people say that Computer language is the only language you learn. You learn to write first before you learn to read. Okay, that is actually a problem. Okay, you learn to write first, so you write crappy code. Okay, if you learn to read first, then you probably will be writing better code than if you learn writing first. Okay, you learn from the really nice, elegant programs. Okay, that the people wrote before. That's probably a better way to learn. But the thing is that, well, what do you mean if you learn by read? You learn to read. Oh, okay, you can look at the things, what this piece of code is doing and understand it. Okay, so when you write your own programs, before you just do it blindly and say, okay, I say, just for example, you have a project in your class. Okay, you say, I just write the code and then submit the code. Well, most likely it will not be working, and you will probably got a 0 or not too many points out of the total number of points for that project. Okay, well, for the if it's a real product, if you just write it without review, without testing, without anything, just write it and deliver it, it's probably not going to be working, and it's not going to make your customers happy. Okay, so the thing is that, well, we know we will be doing some kind of self-conducted review. Okay, but the thing is that oftentimes we have a kind of, because when you do the self-review, you read the program. We all had some experience that I have been looking at this darn program for 24 hours. I couldn't find anything wrong with it, but it still doesn't work. Okay, that's a very kind of a common kind of thing. It's, well, because you wrote the program, and when you read the program, you follow your own logic, how you write it, and you read it. Then your logic may be flawed in some place. You may have some contradiction, self-contradiction there. You may have some holes here, there, and the things. So sometimes that you say, okay, you can have get someone else to help you. Okay, so sometimes actually this happened to me quite a few times when I was working on some of the things. And I think it happened to many of the people is that you got a friend you discuss this with, and you say, okay, I'm trying to do this, and your friend say, why are you doing this here this way? And you say, I'm doing this way because, oh, yeah, that's the problem. By trying to explaining that to someone else, you might find something there. Okay, so essentially what you have there is that you have the independence of view and the independent perspective. You want to get a somewhat a fresh perspective, and so having someone else looking at your program, or you explain that one to someone else, will help in a lot of situations. Okay, so that instead of just doing self-conducted review, you can get some other people to help. There are different levels of help that you can try to just explain this to your friends, and then your friend can ask some questions. That is one level, and another level is your friend can really go through this line by line, logic by logic, and looking at what is going on here, and try to find the problems. Okay, so that kind of independent review will be very, very valuable. Okay, and so you can do that. So because you have some kind of independence and orthogonality of your different views, that will help you with finding the problem. Okay. Well, if that's the case, you say, okay, how about we try to expand this a little bit further? Instead of just having one friend looking at this, we have a team to look at this. That is basically the idea. Okay, nothing very fancy, but it's just a common sense that need to be followed through, need to be implemented, and need to be having some guidelines and some rules that can be followed. Okay, so to do this, actually, Michael Fagan, who was working for IBM at the time in the 70s, started with this so-called Fagan inspection. Okay, figure inspection essentially want you to inspect the software with a team of people, a group of people, instead of just one individual to inspect something. Okay, so a group of people. We'll talk a little bit more about figure inspection and other inspection later on. Okay, the basic structure of that is that well, if you want to do the inspection, you need to select the right kind of people and give them good instructions and give them a process to follow. Okay, so the right kind of people are the people who are not the programmers themselves, because you want to get a different view. But you don't want to just go to the street and grab anyone to do the inspection. Okay? Someone who never heard about Java. Oh, Java is that some place in Indonesia, or is that some coffee or something? Oh, well, yeah, maybe, but that's not the Java we're talking about here. Okay, it's a C++. Why do you have C++, not the F++ or something? Okay, are people just getting a grade C and they get another plus or what? You can't get those people can inspect your Java code or C++ code. You must have some basic knowledge. Okay, and so typically you need to have enough knowledge, but not very intimate knowledge about your things to be inspected. Okay, so you need some general knowledge, but not they should not be the ones who design this code, but they should be generally knowledgeable about this. Okay, and then of course you may be able to have a range of people that some of them are more closely related to this project and this part of the things you are inspecting, and some of them are probably a little bit less familiar with it. That's okay. Okay, so you need a group of people to do it. Okay, and so they are generally knowledgeable, but not intimately knowledgeable about those things, and not the owners of this code of this artifact themselves. Okay, and then you have to look at the numbers. How many people should be involved? Okay, in original suggestion by Michael Fagan, he said about 4. Okay, about 4 people. Okay, the consideration is that well, if you have about 4 people, you get enough different perspectives. Okay, and but you don't have a really big group. When you have a very big group, you cannot really make use of the individual talent as much. Okay, so sometimes when you have a bigger group of 10 or so or more, generally some very vocal people will kind of overwhelm other people. Okay, so you will have a kind of natural hierarchy of the people that play in the group, and then some people will become leaders or become dominators and something like that. Okay, that's kind of what they say. Michael Fagan said, yeah, about 4 people is about right. Okay, so it's kind of like if you like music, and you know 4 is a very important number that in classical chamber music. The quartet is a string quartet is a very important form of music. Okay, so that you can hear every voice clearly, and they intertwine, and they produce beautiful things, and but nothing overwhelm others. Okay, so not like a big orchestra that you will probably want to hear the individual voices as much. Okay, so 4 people. Okay, about 4 people, and there are people who are somewhat familiar but not intimately familiar with the thing, and then you need to give them a process to follow. Okay, a process to follow is that well, you those people, they have different roles. They are generally inspectors, okay, and they will be interacting with their owners or their of the code or of the artifact that's produced, okay. And then because you do have a group of people, you do need some kind of coordination, okay. So you need some kind of a coordinator, moderator, okay, and so some kind of role assignment is necessary, okay. But then you need to follow some kind of process to do this. the process they generally consists of kind of some kind of preparation, some kind of group activity, and some kind of follow-up. Okay, so in the original Fagan process, he said that you need to kind of have some planning as the planning, and then you have 5 steps. But then nowadays, people generally consider planning as one step, so that it becomes 6 steps inspection process. Okay, so you first plan the whole thing out. Who's going to be doing what is going to be inspected, and who's going to do the inspection, and what's the team makeup, and who's going to be the moderator, and so on. Okay, so you plan the thing out, and then before the people get together, doing the group inspection, you need to have some kind of kickoff, and so some overview. So the planning is the first one, and then the next step is some kind of overview. So you will be inspecting this design. So the designer will be meeting with the inspector. So you have a general discussion about what I did this design, this is what I try to do, and give the overview about design. And you guys are going to help me with the inspection, and I need help in this, and this area. Okay, so kind of overview. And so in this case, the designer or the developer will be playing a very important role to try to give the information about the things, and also you talk about their objectives and the intentions and the goals of this inspection process. Okay, planning, overview. And then the next step is that with the planning and the overview, now you have the group of people to do the inspection, and you know who's going to do what. Okay, essentially now what you do is that, well, you will be inspected part A, you will be inspected part B, and you will be inspected B and C, and you will be inspected A and D, something like that. Those are 4 people. Okay, and so sometimes you do allow some moderator overlap. Okay, because some of the part you want more people to inspect directly. Okay, and but you try to achieve some coverage. All the things need to be inspected. At least one person will be inspecting it. Okay. In this case, actually, in the Fagan original terminology, he didn't call this inspection. He called this preparation. Okay. And so you do the individual inspection. In the Fagan original terminology, he called this preparation. So you are preparing for the inspection meeting. Okay. So essentially you're doing the individual inspection. You inspect just one part of the thing that's assigned to you. So each member of the team, inspection team, will be inspecting part of the things that they are assigned to. Okay, and so we do the individual inspection or the preparation. Okay, and then people will come together, have an inspection meeting. Okay, so in the original literature, Fagan called this one inspection. It's the group meeting that are doing the inspection together. That's called inspection. Okay, so you do the inspection or the meeting. Okay, and sometimes in some other literature, people call this a collection. So you come together, collect your thoughts and doing the things. Okay, and then there's some rules about how long it should be, and how you conduct these things. What's the role of a moderator, and someone will be the note taker, and things like that. And then the focus is really look at here. Is the focus is looking at you found this individual problem. You found this individual problem. We try to consolidate the problem, not to suggest solutions. Okay, because once you start to suggest solutions, you easily get sidetracked. Okay, you say this is wrong, why it's wrong, but not how to fix it. That's not really your responsibility to fix it. Okay, so you do this. Okay, and then after this, this inspection meeting. Okay, and then you get the result to the designer or the developer who owns the code. Okay, so in this case is that yeah, in the original one, the designer and or the developer should be participating in this part. Okay, but in other implementations that maybe you do the inspection meeting and then give the result, communicate result separately. That's another variation too. That's possible too. Okay, and then the designer or the developer who owns this part need to have some response. Okay. Yes, this one seems to be a problem. I will work on it. No, this one is not a problem. Why is this not a problem? Okay, so you have the response and the rework. Okay, so that then you have the response and the rework, and then there should be a closure. That so do you agree this is done? Okay, and after rework, is this satisfactory? Do we need to go back run another inspection process or not? Okay, so that's the last step. Okay, so you have the planning overview, individual inspection, group inspection, rework and the response, and then some closure. So that's 6 steps in the figure inspection process. Okay, of course this is a kind of a very quick and high-level summary of this one. Okay, when you actually do it, it will be a lot of kind of individual details that you need to learn about. Okay, so for example, that Michael Fagan had his own company, and oftentimes they work with many different large software development organizations and try to teach them how to do the inspection. Okay, and for example, in my past class, I did have some students who actually went through the Fagan company's inspection training. Okay, so it's not just this 15 minutes training. It's something like a 2 day, 3 day extensive training. So they look at the technique and they perform some of the case studies and they do it there, and then they coach people on how to perform those kind of inspections. Okay, so it's a really, really important the type of activity for quality assurance. Okay, so what people found out is that there are good things and there are some part that some ways of implementation may make it work really well. Some other ways of implementation may make it work less well. Okay, so that's the reality. And so, for example, people found that in the figure inspection process, if you don't really do the preparation, do your own inspection before coming to the meeting, then your meeting is not going to be productive. Okay, the meeting becomes kind of a social chatting session instead of a real inspection session. Okay, so they found that really the number of defects detected through inspection, really most of them come from individual inspections, not from group. Okay, group is really confirmed some of the things, and then collectively, sometimes you also find some problems, but not as much. Okay, so because of that, some people say, okay, let's forget about the inspection meeting. Let's just do individual inspection and report to the developer or the designer. Well, that's a variation. Okay, so that there's a variation that you have the so-called meetingless inspection. You have the inspectors, but you are not having the inspection meetings there. Okay, and then some people say, okay, in this inspection process, it's really asymmetric. Okay, because the designer and the developer whose code or design or other artifacts that got inspected is on the receiving end, benefit from the inspection, but the inspectors, they don't really personally benefit from the inspection process, except that it's their job to do it. Okay, and so you say, okay, sometimes give people incentive to do the inspection is that you can perform some kind of reciprocal kind of things, so that people get an incentive. I can inspect your code and you can inspect mine. Okay, so that kind of you have this pairwise and those kind of actually some of those ideas got carried through to some of the newer development processes like in the agile development process, the test-driven development, programming pairs, and those kind of things. It took a lot of those ideas from those kind of early successful stories, and then come with that. Okay, and then some other people say, okay, inspection, it's maybe a little bit still not so structured. We need to have a little bit more structure to it. How do you mean? What do you mean? Some more structure? Or maybe I can have some of the people focus on certain areas, okay, instead of a general inspection. Well, one of such focus areas is the so-called ADR, active design review. Okay, we will talk about that later on. Okay, so that's a kind of it's an inspection process initially proposed by David Parnas. And so you look at the design review, and then you have to really, instead of just doing a general review, the designer need to prepare some questionnaires, ask the inspectors to follow those questionnaires, and really actively involved in the design review process. Okay, and then some other people said, oh, you told us that you just confirm the problems, but not offer suggestions or solutions. But people often have wonderful ideas. Well, why don't you take advantage of that? Well, some people said, oh, yeah, we try to take advantage of that. We can have some kind of follow-up to this inspection meeting to just brainstorm about some possible suggestions, solutions, and the process improvement. Okay. That is an expanded figure inspection. Okay, actually, originally Tom Gilb proposed that. Okay, so that is called the Gilb inspection. So it's a kind of a figure inspection expanded and more tightly rolled into the overall development process. Okay, so there are different variations and things for this, and so we will be spending a little bit more time on this after the midterm exam, so probably halfway in the second half of the semester, so about three quarters into the semester, we'll be going back and talking about some individual inspection techniques a little bit more. Okay, and so this is something that you can do. Okay, so for example, for your course project, you can consider this is something that everybody can do. Okay, and if you do it in a small group, and maybe you can, instead of getting 4 people, you can get 1 or 2 people to help you with the inspection. That could be something beneficial as well. So that's something really everyone should consider in their course project. Okay, so we talked about this inspection and talking about the defect prevention. Okay, and talking about testing. And then one of the other things that I haven't talked about is not as much here is, well, upfront this thing, people realize when you do the testing, you try to review the presence of fault in the system. If it's there, it reviews it, right? If it's not there, nothing got reviewed. And if it's there, you didn't trigger it, nothing got reviewed either, right? And so when you perform a lot of tests, if you find a defect, great. If you don't find a defect, that's not saying this one is defect-free, right? So the thing is that according to a famous quote from Dijkstra, is that the testing reveals the presence of a defect, but not their absence. You cannot demonstrate the absence of a defect by testing. Okay, it's a kind of like you cannot prove a mathematical theorem by giving a few examples. That is not. That's some evidence. A few examples, but that's not a proof. Like for example, I mentioned about someone said, "Oh, all the odd numbers are prime numbers." Okay, so I look at 1, oh, it's a prime number. Okay, I look at 3, that's a prime number. I look at 5, that's a prime number. Good, all the odd numbers are prime numbers. Well, You didn't look far enough yet. You look far enough, you find a counterexample, right? You look at 9, you find a counterexample. 9 is divisible by 3, okay? So it's not a prime number anymore, okay? So you cannot just give examples, it works, so it's perfect. You cannot prove that. So what other people proposed is that, well, can we come up with something that kind of along the line of mathematical proofs? Yeah. Yes.
So if you test all the boundary values and the middle values you think are okay, can't you just say the whole system is good?
No, you cannot. It's more likely to be good, but you cannot say categorically it's good. Yeah, because without exhaustive testing, you cannot say it's good all through. And for any of the system, it's basically exhaustive testing is beyond any possibility. Okay. And so you say, okay, can I categorically say this is good with, of course, typically you have to, with this assumption, with this something. And that is the idea of a formal verification. It verifies it is defect-free with regard to its specification. Okay, so we can look at we looked at the. Let me see. I skipped that. Yeah, formal method. Okay, so the basic thing is here is that because the formal method consists of 2 parts. Okay, essentially what you do here with the formal method is that you try to formally specify or describe what is supposed to be the behavior of your system, and then you verify it with some kind of a logical mathematical argument. Verify that is indeed the case. Okay, so to show it in a kind of schematically, we are trying to do something along this line here. Let me switch over to the document camera. Document camera. Okay. So essentially what you have here is with the formal verification and the formal specification is that, well, say for example, this is your piece of software, okay? Software module or something, okay? You have a software module, okay? It's supposed to have some certain function, okay? And so what do you need to do is that, well, if you want to, in mathematics, if you want to prove a theorem, prove something, you have to state the theorem in a precise way, right? Okay, so for example, you say, okay, in a triangle, there this kind of relationship, in something that there this relationship, you have to formally state it, okay? So for the program, you have to formally state what this one is doing, okay? So for example, that you say this program is giving this input, okay, and then this one will become a function of the input. Your output is some function of input, some mathematical function of input, okay. So essentially, what you are looking at here is that if you think of this, that if you have one-dimensional input, that's your input, so you have one-dimensional output. So this one is basically give you a mapping from input to output, right? Okay. So mathematical function mapping the input value to some output value. Of course, you have a two-dimensional, higher dimensional things. Well, not such a simple kind of drawing. It will become more complicated. So you have some kind of a mathematical function that's mapping the input to output. Okay, and so that's one way of formally describe it. Okay, so as some kind of mathematical function of this thing. So this one, basically, this software, let's call it A. Okay, so this basically this software A applied to I will map to this O. That's so this software that will serve as this mathematical function to map me from the input to the output. Okay, So that's one way of formally specify it by specify a mathematical function. Then in most of cases, those mathematical functions are not simple trivial functions. Okay, not just doing the square root or something like that. Typically involves a lot of logical conditions. When you involve lots of logical conditions, then those mathematical function will become some kind of thing like under this condition, this one, and so it's all equal to this when this one is the case, when this one is the case, when this one is the case. We have this kind of mathematical functions, right? The discrete functions that with the conditions and the things. You can do those kind of things, okay? But another way of specify this thing is that I say, okay, I can look at before the execution, what is the state, and then what will be the state after execution, okay? So for example, that I'm calculating input is x and the output is the square root of x, okay? So say for example here, square root of x as output. So this is the input, this is the output. Then I will say, okay, can you calculate the square root of negative numbers? Probably not. In this case, for example, we just deal with real numbers, okay? Then you cannot, then you will say, okay, given x is greater than or equal to 0, I will calculate the square root of x, okay? And so what I have here is that I've said this is my input condition, okay? And then what is my output condition? My y is the square root of x, my output, okay? So essentially what I'm saying here is that I have an input condition or precondition before program execution, and I have a post condition after program execution, okay? So I can specify what this program is doing by formally specify the precondition and it's a post condition, okay? And then this is our formal specification, okay? You can specify it by the mathematical function, by the pre-post condition. And sometimes people say, oh, this one is still kind of too abstract. I want to specify the system as if it's going through some kind of different states and eventually reach something, okay? So you, this kind of specification is what we call the descriptive specification, okay? You describe what things is doing. And sometimes you say, okay, I don't want to describe what's the input, output. I want to describe how things happen, how the system should behave. Okay, so for example, I should say this one is a system not really doing much of a computation, but it should maintain the temperature. Okay, somehow maintain the temperature between 70 degrees and 75 degrees, something like that. Okay, so you can describe the system behavior. And the behavior, if it's within 70 and 75, it's doing nothing. If it's below 70, maybe you turn on the furnace, okay, to heat up. Okay, if it's above 75, you turn on the AC unit. Okay, so that is a system behavior. Turn on, turn off different part, and then try to achieve the goal of maintaining the temperature to be between a lower bound and an upper bound. Okay, and those kind of things, oftentimes you say, okay, look at it. Oh, when it is below 70, I do this. When it is above 75, I do this. So you have some kind of state. Okay, so you can use some kind of finite state machines. When it's below 70, do this, and then return to some state, and when with other state, and so something like that. You have a so-called finite state machine can usually be used to describe some of the system behavior. Okay, so That's a so-called behavior description, okay, or behavior specification. You describe the behavior, okay. You specify the behavior instead of just use a descriptive things. This one is a condition, this one is a condition, and you look at under this kind of condition, or in this state, you do this, and in that state, you do that, and things like that. You can use the finite state machines. And once you have this thing, then you have this formal specification. In the other part of the formal method is that you want to formally verify it. It is satisfied by this particular implementation. Okay, so that's the second part. Okay, so the first part is really when you formally specify what's the function of this module, this piece. Actually, you are doing a little bit of a defect prevention, okay? Because the expected behavior is more precisely specified. There will be less chance of misunderstanding of the expected behavior. So you eliminate some of the error sources. So oftentimes, the ambiguity is always a big source for problems, okay, for requirements. Okay. What do you mean exactly by this requirement? Now it's formally specified. You leave less room for some false injection here. So the formal specification part is that you can think of this as a part of defect prevention. Well, formal verification part is something like demonstrate it's defect-free. It's kind of similar to testing, but except you are not focusing on finding the problem, but try to demonstrate it is indeed working as expected. Okay, so let's take a break, and when we come back, I will talk a little bit more about this, and then about the verification part, and then we can move on to the other QA techniques. Okay, so let's take a break for now. Not much. We will talk about finite state much more after. Yeah. You can mention some of those things if you need to change it, you can change it. But if you are familiar with the finite state machines and you want to use it for testing, that's
You can do testing on that. That's a bug and stuff, right? Testing on that.
Yeah. That's okay. That's okay. Yeah. Not necessarily. Some of the open source things are not web-based. Like for example, Linux is really not really web-based. Yeah. You may or may not, but that's okay. If you don't, then you can just test it from the top. Yeah.
So can you use the normal, whatever the general specifications of the web, this must be done because it's so much.
That one is kind of hard to say because even if they don't strictly adhere to that, you cannot say that's a problem.
So the open source software is used.
Yeah. The open source, you do have the access to that.
Yes.
Open source, no, they do have those things typically on the web. You can download. No. When it's open source, then the source code. Yeah. Yeah. And there's some free software. Free software doesn't mean open source. Open source and free is different. Well, you can do white box testing. If you don't have the code, you cannot do white box testing. So that's and also you can do more of the internal things. Yeah, hopefully about the internal.
I don't have access to the 7,000 level section.
I don't know.
Why do you need that?
I haven't posted anything there yet.
Because you can choose, right? There's community included.
Supposed to.
There's
Let me check on my end. I should have all these people.
This thing, it looks at what other after like bugs and things are integrated, it'll change to.
For my other class, I checked and they kind of included everybody because my other class, the OS class, we had about half undergrad and grad, and I had all the people there.
I think they reset everyone's password maybe. I had to go to the office and get one changed.
That's weird.
Yeah. There's something wrong with the servers after this year, I think. I don't know.
I locked down. Oh, okay. I guess I cannot use the return key. So this is the 73. This is terrible. What's this semester? This semester is the fall. 11:47.
I was looking at the calendar, right?
Our
It makes sense, you know, take a look at
let me see.
First one they have like input domain testing, right? And then after the midterm, you have the
I'm on, it shows that I'm on there,
Oh.
but on my computer it shows up as 5,000.
Ah. But
Maybe they're merged.
yeah, they merged. And,
Yeah, because we're supposed to.
But so now like the main thing in the school is asking what's the expected results.
I'll do this now, and then you can see whether you can see it. Let me create an assignment, first assignment.
So I think for following back, so if you can try to handle the exception, right? See if you try to handle the exception. Yeah.
Due date. So I put the due date of the next Monday.
We'll try to handle them. I think we don't need to completely fix them, right? We need to somehow instead of throwing exceptions, we can try to
Okay, I submitted it and see if you can see it from your you can see homework number 1. Oh, so no problem.
So, they're gonna do the consolidation for the homework
They already consolidated all the Blackboard sections.
Okay.
Yeah. And
They still say like the 18 class for mine, so.
Yeah, but you probably that's the kind of become the child section for 701C. So yeah, you should be able to see.
So can you be able to submit your homework from there?
Yeah. She was in 5314 section, and I just posted the homework, and she saw it, and so you should be able to see it.
Oh, see from the home, from Blackboard now?
Yeah.
Okay. See from Blackboard now? All right.
You are in 418, right? Or
Yeah.
something. Yeah, and then you try it and see.
Is valid location, occupied location. You can put stuff, remove stuff, and it should return.
So maybe that's a better way to do it. Yeah. I remember they were talking about some parent section, child section, all those other sections become the child section of the 701C, 7314.
Oh, so you can do option A or B.
Okay, I think it's about time we should go back to our class. Okay, let's go back to our class. And so I was talking about this formal verification and formal specification. So they are together. They are called the formal method. Okay. So there are various different flavors of formal methods or different formal methods people call. For example, that there are some ones that use finite state machines. That's one kind of formal method, and then there, yeah.
For inspection, is the code like executable or is it not executable yet?
Either way.
Okay.
Yeah. So, for example, design you can inspect it. Okay. Requirements you can inspect it. Okay. So when the code is there, before it's executable, you can inspect it. After it's executable, you can inspect it also. Okay. And actually, you can think of that in testing, after you observe the failures, you need to fix the problem, try to find the problem, and that part you may be doing some kind of examination, and could be inspection.
So is inspection mainly trying to see if we get an incorrect output or trying to fix the incorrect outputs?
Not necessary. It could be inspecting for internal logic.
Okay.
And those internal logic may be something wrong, and maybe never really produced anything.
Okay.
Yeah, you can find that as well. Yeah. Okay, so any other questions? Okay, I'll talk a little bit more about the homework and the project later on. Okay, and so I had received some questions about homework and the project, so I'll talk about that later on. Okay, we can defer that toward the end of today's class. Okay, so we talked about this different ways of formally specifying what this software or this piece of software is supposed to do. Okay, now we say, okay, that can be part of the defect prevention. Okay, and then the next part we look at is now this is supposed to be doing this, and can we verify this is indeed doing this or not? Okay, so for example, if you do have a finite state machine, then you can execute your finite state machine. Right? So you can execute a finite state machine by some software that can help you with the finite state machine execution, or maybe you, when you build the finite state machine, you do have some facility to do the tracing the finite state machine. So for example, in that case, you will be able to run your finite state machine and just check certain properties. So for example, with a finite state machine, you can say, okay, I have a finance machine. Here is another two state. Here is the, for example, this is my initial state. And can I reach those two states from here? No, I cannot, right? Because there isn't any link between this part and this part of the finance state machine. Although you say this is a one finance state machine, but actually they have isolated part, okay? And then in that case, you can do things such as check the reachability, check the something that it will be recurring again and again, and those kind of properties you can check. Okay, so because you have a finance state machine, you can execute the finance machine. You can check certain things. Okay, and this kind of a formal method is called the model checking. You have a model, finance state machine model. You could check in some properties by executing a finance machine, by analyzing a finance machine. Okay, so this is one kind of a thing. It's called a model checking. Okay, called model checking. So model checking is actually one of the kind of most successful kind of formal method up to this point, because you do have some automated execution capability come with it. Okay, you can check this, and for example, that you see, is this reachable? This is the initial state. Are all the states reachable? You do this thing. No. Which states are not reachable? Those two. Okay, from here as the initial state. So your proposition say, are all the states reachable? So you say all the states reachable. Now you would say this one, those two are not reachable. You give counter examples. Okay, so you can either verify some property is satisfied, or you produce some counter example. Okay, that the property is not satisfied. When that property is not satisfied, the finance state machine will give you the counter example, and your counter example actually serves as our kind of similar purposes as the defect detection in our testing. Because the counter example said that this part is not reachable. If you wanted something to be reachable, then you have a problem here. You find some problem, you can fix the problem. Okay, so that's you can use this so-called model checking as a finance machine. But in the most classical basic thing, in finance state machine, you have to state something in terms of something can be executed, okay? But not really stated the full functionality of the thing. In this, our original classical specification, we really describe the full functionality. With the full functionality, we can come up with some kind of verification steps, formal verification steps. For example, one way of doing this formal verification is that, well, I'm looking at formal mathematical functions. If you have a formal mathematical function defined for this whole thing, then I can look at, well, my program will be we typically consider sequential programs. When you have a parallel program, so it will become much more complicated. With sequential programs, then what I can do is that, well, I will do this one, 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 and in the sequence. And maybe I have a loop here, and but I do those other things in a sequence. Okay. I have a loop here. So after this one, I go back to here. And then what I can do here is that, well, what is this thing doing for me? What is this thing doing for me? What's this thing doing for me? What's this thing doing for me? What is this whole loop doing for me? And what is this thing doing for me? So I can divide that into the smaller part, okay? So I can do this so-called divide and conquer strategy. That for each of the small part, I can precisely associate what this one is doing. Okay, and so I say, when I have the input-output mapping, I can map this one, to this state, 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 and then I did the mapping from the beginning to the end. Combine those together, I produce this overall mapping from the beginning to the end. It's kind of like with mathematical proofs. We often have built upon some other theorems. We use one theorem to prove another theorem. And sometimes you come up with lemmas and things like that, and then prove a big theorem. Okay? So you can look at those small things and build up those things. So this is one way of coming up with a kind of almost like a mathematical proof. Forward chaining and look at what's the meaning of each small element that can transform our program from execution from one state to another state. Of course, you are not assigning specific values. You are looking at the logical relations, general logical relations between here and here, here and there, here, here, there. The general logical connections and the relations. And so when you, as you do go through this, you oftentimes need to do the so-called symbolic execution. Look at this one, express the output as some kind of function or symbolic values of the input. Okay. So this is one way of come up with this kind of formal verification. Okay, this is the so-called functional approach, because you interpret each small unit as a function, as a small function, and then the overall program verification become a functional composition of those different sequential parts. Okay, so this is the so-called functional approach to program verification. Okay, we'll talk a little bit more about this later on. Okay, and this is a functional approach, and sometimes it's also called a program calculus. Okay, so it's a kind of like a mathematics or calculus for programs, not the calculus for functions and variables and things like that. Okay. Another way of looking at this is sometimes people say, okay, oftentimes I can do a bottom-up approach. Okay, I'm not necessarily connect them all the way there. I look at what's this mean, what's this mean, what's this mean, and then what's this block mean, and what's this mean, and then I try to come up with this kind of bottom-up approach, not necessarily just going through this forward chaining. Okay, when I look at the bottom-up approach, then I say, okay, each of the individual elements, what's this mean? What in terms of its pre and post condition? Okay, so for example, if I do an assignment, what's going to be the pre and post condition? Okay, if I do a if then else, what's going to be the pre and post condition? If I have a while loop, what's the pre and post condition? Okay, and all those kind of things. So essentially, for each of the small components, I will have some axioms. I say, okay, this is beyond argument. For assignment, I assume this one will be the meaning of this, how it transforms its precondition to its postcondition. For if then else and so on. So I have axioms. Okay, so those axioms are like in geometry we have some axioms about, for example, if something is perpendicular to another line, what's that mean? Okay, and if one line is parallel to another line, what's that mean? Okay, so there are some axioms. Okay, so that the parallel lines will never meet, for example, in the classical Euclidean geometry. Parallel lines will never meet. But when you change that axiom, actually you get a different kind of geometry. Okay, so you have axioms and you have some basic rules, and then you make up those things to build up bottom up and build up your overall proof. Okay, and sometimes the people say, okay, I'm more concerned with the execution result, and instead of the input, and then I will find that my specific input can it be accommodated by this program that get me the desired computational result. So a variation of this bottom-up approach is people looking at what is the precondition for some post-condition, okay? And then going through this backward chaining, okay? And get the overall proof. Okay? Actually, most of the bottom-up approach focus more on the backward doing. You focus on the result and look at what's the precondition and what's the next precondition, and sometimes you can extend this to looking at what's so-called the weakest precondition to produce this result. Okay, that's the so-called WP approach, weakest precondition approach, which is a variation of the axiomatic approach, actually. Okay, so those are some of the classical formal verification techniques. Okay, and of course we don't have enough time to go through the details there. And actually, in the U.S., it's not as popular and not as widely covered in the software engineering curriculum. But in Europe, actually, they do more of the formal method, formal verification. Okay, so in some universities they have a full course on formal verification. Okay, and when I was myself a graduate student, actually, at that time we had a kind of I was a graduate student at the University of Maryland. We had half of a course on programming language theory. About half a semester we spent on formal verification. Okay, so something like I don't know 7 weeks or so, 6, 7 weeks on formal verification. Okay, so there are lots of things to cover in there, and it's kind of not an easy thing to do. So that's really it's a difficulty. It's not easy. It requires rigorous training by the people who are performing this. Okay, those people need to be trained, and even if they are trained, you can make a mistake. Okay, and one of the funny things that I have my own personal experience is that in this book, our textbook, when I was preparing the chapter on formal verification, I used the example. It's a kind of a derivative example from some other thing, but not exactly the same example. So I had to come up with the proof steps myself and write the thing. And then when I was teaching one of actually the follow-up course to this reliability and safety, we did use formal verification as a part of the safety assurance. Well, I was going through the steps, then suddenly it dawned to me that I actually made a mistake in one of the steps. So when you do the formal verification, who can check, make sure that your verification steps are correct? Okay, and that's one of the problems. And actually, if you have a program, typically if you have say for example, one-page program, your formal verification of that one-page program itself will be about 10 pages long. Okay, but you can argue this is a once for all. You're doing it once correctly, and then it's verified. Okay, so you don't have as many of the maybe if you want running test cases, you will be running hundreds of test cases, and then those will be hundreds of pages with test case input, output, result, and the things. Okay, but you say, oh, then I can automate those tests to some degree. Well, what about formal verification? Probably you cannot automate much of the formal verification. It's mostly mathematical and logical driven. So you basically you have to have intelligent people doing this for formal verification. So that's one of the difficulties with it. Okay, so generally it has its limitations, but if it's something really, really important, and you can afford to have some highly trained people doing this thing, it's probably worthwhile, okay, to do. So formal verification is another thing that we can try to do, but it also has its limitations besides the fallibility of the people who are performing this. There's also any of the formal scheme, you must make some shortcuts, some abstraction somewhere. Okay, for example, that most of the formal verification schemes, they will not consider round-off errors. Okay, so you consider a real number is a real number, not a multi-byte floating point number. Okay, so the mathematical real number is not the same as our multi-byte floating point number in the internal computer representation. Okay, so there are some of those things that you cannot really, because when you do the abstraction, you cannot take care of that. And also, in the program execution, you have side effects. None of the formal verification schemes will take care of the side effect. Okay. So there are some limitations to the formal verification, but still it's something that is worthwhile to consider, okay, as one of the techniques that to guarantee or assure the quality of your software system. Okay, so let me switch back to the computer, and then there are the wrong one. Okay, we talked about inspection, testing, formal verification, and then there are a couple more that we want to talk about. One is the fault tolerance, and one is some of the safety assurance part. Okay, so fault tolerance idea is actually fairly straightforward, because when we look at a lot of things we deal with in daily life, we try to have some redundancy so that if we have lost something and we still have some backup to it. Okay, so for example, that we talked about you have multiple airplane engines and you have things that you can recover to, you have backup copies of your files and those kind of things. You can think of this, those are some kind of built-in fault tolerance capability. But you can apply the same idea to software. Okay, so you can, for example, that you can outvote the wrong results and things. Okay, so for the fault tolerance, you try to have some kind of redundancy or duplication, so that if some part is not working, your overall system may still be working. Okay, so you have fault in the system, but that fault will not be leading to failures, or that fault will lead into a failure with maybe minor impact than a major impact. Okay, so the most common kind of strategy for fault tolerance are two strategies. One is some kind of a direct redundancy, another is a kind of a re-execution as a redundancy. Okay, so this is probably can best be explained by looking at a couple of pictures. Let me see, which chapter is it? Fault tolerance.
Chapter 3?
No, not chapter 3. Have a chapter on the formal verification, fault tolerance. Okay, 16. So I find that chapter 16. There are a couple of pictures. The first one is this picture. Is the redundancy through the inversions, NVP inversion programming. Okay, so essentially what you do here is that you distribute your computation or decision making or whatever kind of things to multiple versions of the program that have the same functionality. Okay, and then you try to get some decision unit to decide based on the kind of all the output from all the units, what is going to be the output for this overall unit. Okay, so for example, that we mentioned about this addition. You did 2 plus 2. Ask one person uses a calculator to calculate 2 plus 2, another one uses a PC, another one uses a smartphone, okay, and then another one uses a supercomputer, and another one uses a paper and a pencil, okay, and so you got the fault tolerance there, and then probably in this case most of them agree that's 4, and if someone says it's a 5, you can outvote that one. Well, there also in this case is that you can have look at the result, have a majority rule, a vote, or sometimes that you can relax that. So because we mentioned about that if you make a mistake, you're more likely to make a unique mistake. Okay, if you agree on something, you're more likely to be correct. So I got 5 people calculate something. Okay, not 2 plus 2, maybe something much more complicated. I got back maybe 4 different answers. 2 agree, and then there are 3 other answers. In this case, I probably have a little bit more confidence in those 2 that agree. Maybe that's the correct answer. If they did it independently, and they come to the same conclusion, they are more likely to be the correct answer. Okay, so that my then in this case, my decision unit basically say as long as there's at least 2 agree, I can give that one as a result. But what if I got 3 answers? 2 agree, another 2 agree, and 1 disagree. How do I do it? Then I don't know. You have to come up with some decision algorithm to do this. Okay. So in this case, is that if any one of this version is not working, you have a fault, or you have some dynamic situation that's make it not working, then no problem. You still have a fully functional system. You can say, what about this decision unit? If this one is not working, the whole thing is not working. Well, that's a single point of failure. You do have a single point of failure. But the thing is that generally you can argue this is a much simpler unit than those units. So you can be more likely to assure the quality of this part than assure the quality of those other parts. Okay, so you can do this, and then this MVP will help you get your result, even correct result, even you have some fault in the system, and you have some local behavior deviations, but you will not manifest that local behavior deviation into the global behavior deviations. Okay, so in some sense you blocked some faults from becoming failures. Okay, so that's the fault tolerance. You tolerate some faults here. Okay, and then another general solution is this kind of redundancy over time, redo some of the things. That's called a recovery block or checkpoint and recovery strategy. Okay? And actually, a lot of times, this is a strategy we employ for backing up things. Say your files, you back up your files, you back up your important documents and things, and make copies of those things. Okay? And so when there's something go wrong, you can go back, reload your thing. Your file is one example. Okay? And so a lot of times then when you are working on things, the system will allow you to save the result. Okay? And you're working on an email, you're working on something, and you have the partially save the result, and then if the system goes down, and then you can go back and go to the save result and start from there. So you don't have to start from scratch. So that's the same idea. Okay, so you basically here is that you periodically during the normal execution flow, you establish a checkpoint or recovery point. Okay, and then you continue. Get another checkpoint, get another checkpoint, get another checkpoint or recovery point. And you save some of the dynamic contents of this latest checkpoint or recovery point. Then, if your system experiences some trouble, there's some failure, then you go back, get your saved dynamic contents, reload it, and rerun it. So that's the basic checkpoint and recovery. Okay. So what you have here is that you say, oh, this looks like a very simplistic strategy. What if I rerun it and it fails again? Well, if you do have some internal fault that caused this thing and that fault got triggered again and again, then you will have a problem. You will not be able to pass that point. But if it's some kind of dynamic situation, when you rerun it, it's probably not going to have the same exact dynamic situation again. So you'll probably be able to pass that point. Okay, that's why we reboot our computers all the time. Right? Okay, we reboot our computers. We should sometimes blame Microsoft for it. Okay, but oftentimes it fixes the problem because actually after running something and maybe their garbage collection has a problem, their communication routine has a problem, maybe some other things have a problem, and when you reboot, you have a clean slate, and then you will be able to do whatever you will not be able to do before rebooting. Okay. So, but this in this case is that you can redo it. You don't have to redo from the very beginning. Redo from a kind of a recovery point. Okay, so that's the general idea about fault tolerance. Of course, when you do the fault tolerance, doesn't matter you do this MVP or you do the recovery, checkpoint and recovery, it will be more costly than without the fault tolerance. Right? With MVP here, that you will have all those parallel versions. It will be costing at least n times more for that function, and maybe more than n times more, because you need to have some coordination and the decision unit and some of the other things. Okay, and also with software, can you make sure that they don't fail on the same input? So for the hardware, we generally rely on some physical characteristics so they will not fail on the same situation. So when you have multiple engines, right, and you don't generally assume that one engine failure and another engine failure will be tightly correlated. They are independent units, so they are probably not that tightly correlated. But with software, well, one of the things that we say you should do is reuse. Well, if you reuse here, it defeats the whole purpose of inversion. You have the n exactly the same version of a program running, then probably you'll get exactly the same wrong result. Right? So reuse is probably a very bad idea for fault tolerance purposes. It's generally a bad idea for safety critical systems. Okay? Because you want to have some kind of independence between the different things so that they can balance or counterbalance each other. Okay? And so we can see that when you do the fault tolerance, it will be very costly, and you have to assure their independence. And then some people say, that, okay, how do I assure their independence? I can have certain process guarantee, some technology guarantee, and some with this and that kind of guarantee to make sure it's independent of each other. Okay, with recovery blocks like this, you will allow extra execution time. Right? You need to have the overhead of periodically established checkpoint, and then you will also need to have the luxury of being able to do the re-execution. Okay, so you need to have a spare capacity, and you also have to incur some overhead to do the checkpoints. Okay, if you do checkpoints too often, then you spend too much time, too much of your resources on checkpointing. Okay, that's probably not worthwhile. But if you don't do it often enough, each failure will be very costly. Each time you experience a problem, you will go back, way back, instead of going back just a little bit way. Okay, so you have to kind of balance between the two. How often is often enough? Okay, So those are some of the issues that you have to deal with. But generally, they are very expensive, and they also have their limitations. For example, the checkpoint and the recovery, if you have a problem, then if you have a fault, then you are likely to trigger that again. So sometimes you use a combination of checkpoint recovery and the MVP. So you have, instead of running all the versions, you have a backup version. If something fails, use the backup version instead of using the current version. Okay, so that's a kind of there are many different ways of trying to design this thing and try to make it work better. But generally, it still has its limitations, and then it's going to cost a lot more. Okay, so for so-called high assurance systems, the system will need very high quality. You can probably need to consider those fault tolerance and other things. Yes.
So the checkpoints are restore points?
Yeah, the checkpoint is the restart point. Okay, so you are not going to the very beginning. You will go back to this point and restart here. Okay, so that's the general idea of fault tolerance. And then there's also some idea about for safety critical systems that you want to have some additional guarantee. Okay. For safety critical systems, generally we have several definitions. Is that we have some of the concepts related to the safety critical system is that we have the so-called accident. Okay. Accident is basically a failure with very severe consequences. Okay. So when it has a very severe consequences, we can call it an accident, and then the system may have this accident. We call this safety critical systems. Okay. And typically it involves, because we're talking about safety, it involves people's lives and some other major things. Okay. That major damages. Okay. So for example, that if you think of this the air traffic control system, that is a safety critical system, because if it's malfunctioning, then you may have a traffic accident. Okay, that autopiloting system. Okay, in that case, medical equipment software for medical equipment controller. Okay, so radiation therapy. That one of the very famous kind of software-related accident is the CIRAC 25 accident. It's a radiation therapy machine. Okay, and under certain conditions, that thing can malfunction, and they deliver massive dose of radiation to patient, okay, and actually killed several patients. Okay, so that's a software problem, actually. It's a software problem because under certain conditions that their radiation dosage was not checked, and way higher the dosage than anybody can tolerate could be delivered by that machine. And so in those kind of situations, then what we do is that we try to analyze what's the precondition to some of the things. Okay, so for example, that you investigate some traffic accident. Okay, and say you look at some traffic accident and a collision between a car and a train, for example. You say, oh. The driver was driving by and hit by a train, and you, for example, you do have that cross guard arm that was not done. It's malfunctioning. So the driver didn't pay attention and then tried to cross the train track, and then the train came and hit the car. Okay. So in this case, that signal that a rail crossing arm was not done is one of the preconditions that lead to the accident. Okay, so that's one of the preconditions. The precondition is something associated with it, but it's not necessarily a guarantee for accident, because when it's not done, maybe you have a very fast race car and you can pass through it. Okay, And they even had those situations like in some movies that the train is passing and then you can crawl under the train and you pass it through if you have that kind of a car. Well, yeah, it's not guaranteed for accident, but when this real crossing arm is not done, it's probably one of the preconditions to accident. And then you can say, can I make sure that my control software make sure that whenever train is coming or whenever train is within whatever distance, this arm need to be done. Okay, so you can eliminate this precondition. Okay, and so what we do with safety assurance is typically we try to analyze the hazard. Okay, so the preconditions to accident. Okay, through various analysis techniques, we'll cover some of them a little bit later on. So, for example, you can use the fault trees, event trees, and various other things, and look at the preconditions, and then try to either eliminate some of those preconditions or weakening the link between those preconditions and your accident. Okay, and even if you have some of the accident, you try to reduce the damage. Okay, so there are lots of things you can do there. Okay, with safety critical systems. So how do you ensure the safety of the system? Okay, and actually, we will be having a follow-up course in that area. So next semester, I'll be teaching the software reliability and the safety course, 8317. So if you are interested, we do have that follow-up course. We spend about half a semester on reliability-related topics and about half a semester on safety-related topics. Okay. So that's the kind of a survey about all the major quality assurance techniques. So going back to this picture, we say, okay, we have several lines of defense. Okay, so we can work on the defect prevention here. We can work on the defect removal when the faults are already committed, they are already injected into the system. Or we can try to tolerate some of the faults or try to weaken their link from failures to accident, or reduce some of the conditions, or weaken the link, or contain the damage through the failure, some kind of failure containment strategies for safety assurance. Okay, so those are the things we will be discussing throughout the semester, and those will be the things, a selected subset of the things will be the ones that you will be doing for your course project. Okay, and actually let me stop here for now. We take a break a little bit earlier, and then when I come back, I'll start talking about your project and your homework, and then I will try to finish up the other two chapters from the first part of the book. Okay, so let's take a little bit earlier break, and then we'll come back and talk about those other things. Okay. Oh, yeah. It's chapter 11. It should be 12.
Oh, okay. Because I found
Oh, no. It should be 14. Yeah, because 13 is rule, 13, 14, 15, 16 are the defect prevention, then inspection.
Well, because I found formal method
Yeah.
in chapter 3.
Yeah,
but it goes into more detail.
Yeah, much more detail.
Oh, okay. So you said 14.
14 or 15.
Oh,
that's 14, that's for 15. Yeah, so that's why I said that so we briefly talk about the things. Yeah, that's the formal method. This is the formal method.
Oh, okay.
Yeah, this is the chapter.
Okay. Thank you.
you put it on the website.
You put on both of them.
Yeah, both.
So it is point two, 1 point almost
Monday.
1.3.
I done G chart. Yeah.
1.3 feet.
Did like all the drawing in class.
Use a chip.
Just discuss. Yeah, very broad topic. Like other classes, we can do math problems. Like algebra.
Use a checklist in section 1.4 and the person goes to CP's review that.
I know that.
Just double check your numbers so you know
Numbers.
numbers.
Whoever, the guy that makes the PowerPoint, I don't remember. I think that he'll probably use that, and then if he needs add-on, then he can pick, like, outsourced or non-outsourced. I think. No, like, that was a great diagram, so I think.
That's the checklist.
Yeah, but see the thunderstorm. That's why. Did you? I don't know where it is that exactly.
He's talking about
Like,
when he gets back.
I want to say it was over the
Parkinson's, yeah.
And it was just
something.
this part, this
Yeah,
part.
we haven't,
Like, everything was fine.
timeline. How the question was.
Oh, okay.
30 minutes.
That was fine again. Huh?
Yeah, I think it happened. Either Saturday or Friday.
I think like Saturday morning, it was kind of cool and wet.
Yeah, it didn't go that far. Like, I was driving up Point, it was like pouring, and I crossed it.
Yeah.
And then like the windshield wipers were on full blast. Like, as soon as I crossed, I turned them off. Like, there was no more rain. It was really cheery.
I guess the real question is.
Yeah, it was.
I've come back. One day I was driving.
Like,
But,
like you can, I can, you know, everything.
and there was like, seriously, I was about 70 for 30 seconds maybe. It was just like, and on either side of it was 30 seconds. There was absolutely nothing.
You're coming in process?
Huh?
Find the answers online and save it.
No, look up how to do it online.
Zero side will break and it'll come back up.
I mean, cause some, you know, some of the stuff just hadn't done in like forever,
That's
you know
what we
what I
do.
mean?
That's what we do.
That's the problem, like, I don't remember that,
Now we can do
they said to be prepared, like, do it big enough behind. So I'm just looking at, like, how the problems have. Chapter 10.
What do you want to see?
plastic cloth, very bottom, it's like the molecule. Yeah.
I think it's probably.
Because the thing is like, when you put some on rockboard too, so you can always go through and just.
And also answer that.
I know
It's
it's
really
hard.
common.
As far as, we wasn't calling behind.
Discuss something.
And then wisdom, finance.
Yeah.
I don't think that would be good. What he's gonna say, come up with stuff, and he's gonna say, what he's gonna study plan.
This week's assignment.
I think honestly, I wanna do, I wanna see if I can find.
He says for the proposal,
You think we can meet in person?
a rough schedule. I don't know how to make a rough schedule for them.
What do you mean, right on the schedule?
A rough
I
schedule.
think we should meet in person, like from the beginning
Oh,
of
rough
the
what?
proposal, so we have a proper plan.
For the project. So what are you gonna work on? Week one. What are you gonna work on?
Well, yeah, so.
Those are what he wants to, like, if, like, if he wants us to get to the state of work order, then he needs to say what we should have done at what time.
I think you need to do that.
Yeah, I'm gonna be doing that myself, you know, so I'm gonna go first. Yeah, that's my professional work.
Okay, let's go back to our class. And so what I want to do next is to first to talk about our first homework assignment, and then talk about the project, and then I'll see how much time we have, and I try to wrap up the other two chapters, chapter 4 and 5, from the part 1 of the book. 4 and 5 are not terribly important, but they do have some kind of things that you should be aware of, but we probably won't spend too much time on those. Chapter 3, we did spend a lot of time, because we really, when we did chapter 3, we used, as I said, used chapter 3 as an anchor, and we kind of went to many of the other chapters talking about in much more detail than in chapter 3, but not as detailed as in those individual chapters 13 through 16. 13, 14, 15, 16, they are the defect prevention and process improvement. That's the 13. 14 is the inspection. 15 is the formal verification, formal method, formal specification, and formal verification, with focus on formal verification. And then there 16 is fault tolerance and safety assurance. Okay, so we did cover some of the material from those chapters, but not to the level of details of those individual chapters. Okay, but we did cover more than just what is in chapter 3. Okay, so you might want to browse through those 13 through 16 a little bit. Okay. And so in terms of homework assignment number 1, I can switch over to the computer here. I have posted a link in the Blackboard, and so everyone should be able to see that in the Blackboard, so you will be submitting that in the Blackboard. But in Blackboard is basically a link, and then ask you to submit things there, but the assignment itself is posted in the class webpage. Okay, so there are 2 parts to this homework. Okay, and second part is the easy part. I shouldn't say the easy part. It's the more straightforward part. Okay, it's second part is some of the questions from our textbook. Okay, so problem 1.3 and 2.6 ask you to discuss those things. Okay, and actually 2.6 mentioned about some software quality engineering. Even if we don't cover it, you can read a little bit of chapter 5 and should be able to answer it. Okay. 1.3 is really talking about some of the necessary background you should have to be successful in this class. And so I almost every semester I assign 1.3 to people because I want people to look at their own background and their preparation for this class. If they need to kind of get some additional preparation for this class, they can use this one as a kind of self-examination exercise. Okay, so that's fairly straightforward. Then the part 1 is a little bit more complicated. It's a required work for graduate student only. The part 2 is everyone is required to do it. Okay, so that's why I didn't give a point scale. So the for undergraduate student, because in their Blackboard, I have to assign a numerical value for the points. So I set 10 points. So for the undergraduate student, so those 2 questions from the book will be worth 10 points. Okay, but for graduate students, they are worth probably half. Okay, and then the other half will be from this part A, part 1. There are 2 options. Okay, so that's another level of complication. Okay. So I would prefer you to do the option A, if you can. Okay. So option A is critical analysis. Essentially, now we have talked about what is quality, what is the quality assurance, and what are the different quality assurance activities people can do in their software development, maintenance, and evolution process. Okay. And including the support, evolution, and maybe phasing out. So what I want you to do is that if you work for a company or you worked for a company before, and you don't feel uncomfortable talking about their QA practice about that company, then I would like you to performing a critical analysis of what they are doing with QA. Are they doing a good job, bad job? And that's basically that's it. Okay. But then there are some specific pointers I want you to consider. For example, that when they talk about quality, from what perspective they really care about quality. Okay. From the customer perspective, or from internal perspective, or what kind of a perspective. And so what's their definition of quality? When they define the quality, from what kind of perspective, what kind of area they care about? They care more about reliability, capability, usability, or what? Okay, and then when they care about those things, how do they keep track of those things? How do they measure those things? And then how do they assure those things through testing, inspection, formal verification, fault tolerance, or whatever? Okay, and so it's a critical analysis of the situation in that company or in your previous company. Okay, of course you say, okay, I work for some defense company. We work on classified project. Okay, I don't want to talk about our quality assurance. Fine. If you don't feel comfortable talking about it, then don't. Okay. If you feel comfortable talking about that, I prefer you to talk about that, because that's something you are familiar with, and you can examine it from different perspectives with a critical eye based on the material we have covered so far in our class. Okay, so that's the critical analysis, and then with the critical analysis, I want you to write a kind of a short essay about this, report this thing. Okay, and so that's the critical analysis part. Okay, and I said that your summary or essay should be around 2 to 3 pages. Okay, And sometimes people write 4 or 5 pages, that's okay. But if you have 50 pages, so that's probably, I don't expect the grader to read 50 pages for this thing. Okay? But if you have a little bit more than 2 or 3 pages, that's fine. Okay? But if you have something like a half a page, that's probably not a good job. Okay? Yeah, I don't think you will receive full credit for half-page summary, okay, critique. Okay? And so that's, but mainly we look at the contents of your summary critique, critical analysis. Okay. If you feel uncomfortable to do this analysis, okay, because of whatever reason, because of some sensitivity of the nature of the business, or you're a nice guy and you don't want to criticize your own company, and or whatever reason. So you don't feel comfortable, you want to do that, then I give you another option out. Okay. So, or for some of the full-time graduate students, if you have never worked for anyone before, not even in an internship or in a university programmer job, then it's probably not a good idea for you to discuss what is going on in those companies. So my option for you is that you can choose one of the chapters among the, most likely chapters 13 through 16, okay, and write a summary of that chapter. So read that chapter and write a summary of that chapter. The summary should be your own summary, not the summary from that chapter and the chapter summary, not that chapter. Okay, so your own digested summary of the chapter. Okay, you don't have to trace through each of the section by section summary. You give an overall summary of the chapter, what this chapter is about. That's it. Again, about 2 or 3 pages. If you produce a 50-page summary, that is by definition not a summary. Okay. Yeah, it's a more than chapter, so the definition is not a summary, and so probably you will not receive a very good grade when you have a summary that's long. Okay. And so that's a homework number 1, and it's due for the on-campus in-class student next Monday, the coming Monday, and for the distance student, you have until Wednesday to submit your homework in the Blackboard. Yes.
Like 1.3 checklist, you actually need that.
Oh yeah, you produce a checklist. Yeah. And if you think of some of the things that you are good at, some of the things you are not good at, so you can list. And some people say, I checked everything and I'm good at everything. That's good too. Yeah. So I trust you. So, yeah. Any other question about homework assignment? Okay. You should see it in your Blackboard. Okay. So they did merge the Blackboard together, and so whichever Blackboard section you see, and you should be able to be. I posted in the 701C, but seems to be they had this kind of section relationship with parents section and the children section and things like that, so you should be able to see it and submit your homework there. Okay. Yeah. Right.
It's like number 2.6 is
Uh-huh.
what the relationship quality assurance engineering
Uh-huh.
quality. Is that like a personal view of it, or is it more like
It's more for our typically those kind of things is from like 4 or 5 lines to a page or so. Yeah. So whatever you think that's enough to answer that question. That's the kind of different from an exam. In exam, if I ask that thing, then I will have a little bit of space left for you to write down. Okay, and if I left you 1/3 of the page, I expect you, about 1/3 of the page, not one line, but not the whole page. Okay, but if you go over that a little bit, then you can always use the back of the thing to write some more. But generally, expectation is that 1/3 of the page should be enough to answer that. I think you have a question there.
So for the background option, like you said, like you can do the work experience within our organization or company. So every project has a different way of qualification.
Yeah, you can focus on whichever one you want to focus on. Yeah. It's up to your decision. You can focus on one or you can focus on the general practice. It's up to you. Yeah.
Is your exam like a lot of writing like this?
No. Okay. We'll be posting some sample exams. Okay. And so the sample exam, okay, I can talk about that like that. The exam, we have 3 types of questions. The first type is multiple choice, so no writing. Okay. That's just your one best answer. Okay. And the second one is this type. Okay. And typically, I have a couple of questions that give you half a page or 1/3 of a page to answer something, discuss something, compare something. Okay. So that typically 1 to 2 pages of that, 1 or 2 sets of questions of that. And then the third type of question is more of the technical question, or the problem-solving question. So I might be giving you a description about a problem. I want you to test it. Okay. I may give you a pseudocode. Okay. Or I may give you a description of a program. I ask you to design a test case based on whatever testing technique to do testing. Okay. So that's usually those technical questions will be really the one with the most points. Typically it's halfway. It's I have everyone a lot of 1 sheet of paper to bring in whatever you want right now. So that's an example. Okay, so we are a little far ahead of ourselves. Yeah. Okay. Any more questions about the homework? Okay, now let's move on to the project. Okay. So previously, I talked a little bit about the mechanisms about the project. We have the 3 parts: a project proposal, a project summary, a presentation, and the project report. Okay, proposal, everyone has to submit a proposal. Everyone has to submit a report. But the summary presentation part is optional for the undergraduate students, but required for the graduate students. So, but you can submit a summary without a presentation. But if you can't give a presentation, I would highly encourage people to give a presentation so that we can share the learning experience, and oftentimes that can be a valuable part of the class. Okay. So if you want to give a presentation, it will be in one of those last 3 classes. Okay, so will be our last class is after Thanksgiving, I think. So and we'll have 1 class after Thanksgiving and 2 classes before Thanksgiving. So in those 3 classes, if you want to give a presentation, it will be in one of those 3 classes. And for the campus student, I will ask you to give it before Thanksgiving, because so distance students, they have a little bit delayed schedule, and so if they want to give a presentation, I give them the first choice for the time after Thanksgiving. Okay, so that's the kind of mechanical part, logistic part of the project Okay, now let's look at what kind of project I want you to work on. Okay, so as I mentioned, because we'll be spending a little bit more than half the time on testing, so everyone must do some testing. Okay, so that's a basic requirement. Everyone must do some testing. If you just do testing without doing anything else, fine. If you want to do some testing with some inspection, with some defect prevention, that's fine too. And with more of the defect analysis and improvement, that's okay. But if you want to do those other things, you still need to do some testing. But if you do some other things, you maybe reduce your testing part a little bit. But you still need to do a little bit of testing. Okay. So in your testing, what I want you to do is find something to test. Okay. I mentioned about your something at your work. Things at your work probably is too big to test the whole thing thoroughly for this project. So you can take a small piece of the thing you work on. Okay, that's one way of picking that. Another way is picking the whole piece, whole thing, but at the high level. Okay, not at the very detailed level of every component. At the high level with all our usage and things like that. Okay, so this is looking kind of like in our critical analysis. If you're working on some classified project and you say you cannot discuss any of those things, okay, then you submit a report. I say I did a great job, but I cannot discuss it. Well, you will not get a good grade in that project. It doesn't matter. I cannot take your word for it. There. Okay. You do a great job, but I cannot discuss it. Then I can only give you 0. Okay. So if you something you do, you must be able to discuss. Of course, I won't ask you to disclose the details of all the things. If it's something with some sensitive information, proprietary information, you can discuss the things in general terms. But the testing part, you must discuss in technical terms. Okay. So what kind of testing techniques you use, and what kind of testing test cases, and what kind of testing results. Okay. You don't need to give the specific numbers and things, but you have to give the testing results. Okay. And the results you analyze is this working well, not working well. Okay. So if you don't feel comfortable talking about those things at your work, then don't use it. Okay. But in general, if you're not sure, you can always check with your manager. You say, I'm doing this course project, and they will ask, the professor will ask me to at least disclose the general function about this thing and discuss some of the testing related technical details. If you don't think I should use this, then I'm not. Okay, so discuss with your manager if you're not sure. Okay, and also be conservative that if you're not sure and you don't want to discuss with your manager, then don't use it. Okay, if you don't use it, then you can use something else. Use the past course project. You can use someone else's project to be a very nice guy and be the tester of your friend's project. Okay, so help your friends out. And or if you don't want to do that, and you can always test something that you use. Everyone is using some software. Okay, you can test on something you use. Something you use, most likely you don't have the source code. Okay, so but that's okay. You can test it from the black box view, usage view. That's fine. Okay. Or if you want to get some exposure to white box, look at the inside. Then, and you don't have anything appropriate, then you can find some open source programs. They have a lot of open source programs. You can do a search on the open source there. You'll find a lot of open source things, and there are a couple of open source hosting places that they put a lot of open source projects there, like OpenForge fresh meat and a few others. So then you can do the web search and for open source software. Okay. And by the way, open source are not the equivalent to free. So something free software not necessarily open source, and open source software not necessarily free. Okay. And so open source basically means that the source code is available to you. Okay. And most of the times the open source is the ones that people, the volunteers contribute to those things. Because companies, they typically don't put their code out unless there are cases they do. Like there's something from IBM, from Sun, and they actually put it as open source things out there. Okay. Yeah, Linux originally is really they have a company, the Red Hat, and the with some of things, but the origin is just purely open source. Yeah. And so you can get some of those things that you can test, or sometimes people want to test. So not necessarily just traditional software you testing. You can test some of the other things like games. Yeah. From time to time, I have people testing some games, and some people test some web applications, websites. Okay, you can apply the same kind of testing strategies. One of the requirements I have for you is when you do the testing, you should try at least 2 different techniques. Okay, and ideally, if those 2 testing techniques will be somewhat different, will be better, so that you get a better exposure to a variety of things. Okay. If the 2 techniques are very close, then it's probably not as good a learning experience. Okay, and then we will be talking about many different testing techniques. For example, partition, equivalent partition, boundary testing, control flow, data flow, finance machine testing, and then we have several of the usage-based testing. Okay, with the basic usage profile, operational profile, or user Markov operational profile, and things like that. So those are the major testing techniques that we kind of briefly talked about them, and we will be talking much more. So based on our brief discussion, or maybe based on your browsing through some of the things, you can select some preliminary candidates of the testing techniques you want to do. And remember, each of those testing techniques, maybe you have a black box version, you have a white box version. So I want you to check whether you want to do the black box partition test or white box partition test. Okay, for example, when you do a black box partition test, like the partition based on the kind of external input or external function. Okay, and when you do the white box partition, then it's a partition based on some internal things. Okay, internal components, internal structures, and things like that. Okay, yes.
We can use either the box or white box. Both technologies.
You can do both. Yeah. Yeah.
Can I do like 70% white black box?
Yeah, it's up to you. Yeah, up to you. Yeah. And sometimes people actually having a comprehensive strategy. That, for example, one of the common strategy people use in the past project is because they say, okay, from the user point of view, I want to find out this is a software system, which part they really use very often. So I perform this kind of usage profile, and then that is like the top level model. And then I found out that this part, XYZ, is used really, really often and very important to most of the customers. I will do white box testing on XYZ. Okay, so that's a kind of white box I use finance machine to test this. I do the control flow of this XYZ module. Okay, that's something like that. So that's so in that case, that you have a kind of not only trying out different testing techniques, you actually have a hierarchical kind of combined strategy of testing. Okay. So that's the testing part. And if you, as I mentioned before, if you want to form a team to for this semester, then it's probably not a team project. Okay. But yeah, well, there are several things that you can do as a team, so you can focus on different areas. Okay, and or sometimes you you can do a lot of other things together. For example, that you can do the inspection, and you can do some of the testing. You one person focus on maybe usage based, and one person focus on the white box, and something like that. And then when you do the result analysis, maybe you can use the various different quality reliability models to do those analysis. Okay, so that's up to you. But the thing is that, as I said, testing, you need at least 2 testing techniques. So if you have a team of 2 persons, if you're mostly doing testing, then double it. Okay, and but if you're doing testing and you're doing a lot of extensive analysis, that's okay. Probably you don't need to have all the testing techniques, but you have to do enough result analysis and quality modeling to justify the formation of the team to do this. Yes.
So for the team, like, can we apply the same testing method or something like double the quantity of functions in the method?
I think generally I want you to see a little bit more variety. Yeah. So yeah, that's my answer. And so in the past I did see quite a few 2-person teams, but typically I don't think 3 or 4 people teams is a good idea, because I want to see you doing some individual testing and things. So unless there is a very strong reason, I don't think you should have a team of 3 people or 4 people or more. Okay. But 2-person teams are very common, and generally you can do a little bit more than a single person project, and go into more depth in some areas. Okay, and a little bit more variety as well. Yes.
Can we start the testing before we submit the proposal? Or do you think it's like
Well, I want you to I don't want you to waste your time, so I want you to give a proposal, and I will give you feedback. Yeah, so the proposal is not really formally created; it's really more for feedback, and the summary also. Okay, the summary is for sharing. The proposal is for feedback. The real project grade will be from your project report. Okay. So that's actually one of the things in the past. A couple of people argue with me that my project grade is this and this. I said that's the wrong interpretation, because they say, okay, your report you use the 10-point scale, and the proposal and the summary I use the 1-point scale. So they say, okay, I got 2, 1 out of 1 here, 1 out of 1 here, and then I got 6 out of 10 here. So I got whatever. That's not the grade. Your grade is 6 out of 10 in the report. And you got 6 out of 10. Okay, and that everyone should get that 1 out of 1 for the proposal and for the summary, because that's the part I asked you to submit, and I will give you feedback. So the so that's the project, and if you want to do a little bit more on the other side, you can do that other side too. So for example, you can do a little bit of inspection. Okay, you can do somewhat thorough defect modeling, defect analysis, and quality modeling. Okay, because once you get the result, you can do more of the defect analysis and quality modeling. Okay, and so if you want to do those parts, focus on those parts, you will still be required to do a little bit of testing. Okay, and but if you're doing exclusively testing project, at least you need to try 2 different testing techniques. Okay, so there I mentioned about that. So the proposal itself. Okay, so you should start thinking about this and start writing that probably next week or so. And it's about 3 to 4 pages. So that's what I said. And if you need twice as much, I will still read it. But if you have 3, 4 times, 10 times, then I reserve the say if you have more than 10 pages, I reserve the right to read only the first 3, 4 pages. Okay, and but if you have less than 10 pages, I'll try to read the whole thing. Okay, and so essentially, this is the structure of your proposal, which will be the same as your structure for the report. So you should have some kind of title. You testing what? Okay, and you had one paragraph of abstract, which should be an abstract, not a background information, not an introduction. Abstract sometimes is also called executive summary. Okay, so it's really summarize what you will be doing in this project. Okay, so it should not be something. Oh, I'm working on this game, and this game is doing this, doing this, doing this, doing this, and you have 3 people play this game, and 4 people play this game, and that's not the abstract. Abstract is say I'm doing testing on this game. I'll be using black box testing, using using public control flow for this one, and I will obtain some result, and I'll analyze the result and see if I can follow up on this, improve this game. So that's a kind of like an abstract. So basically, it's a very high level summary of your whole project. Okay, it's not a summary of the software you're testing. It's a summary of what you will be doing for this project. Okay, so a very high level summary of that. One paragraph, 4 or 5 lines, most likely, and if you need a couple more lines, that's okay. If you just need 1 line, that's probably not a good abstract. That's a title. Okay. More like a title than an abstract. Okay. So introduction, you can talk a little bit about what you are going to do, what kind of thing you are going to work on, but not the details. And then you should have a little bit brief background information. That is one of the common mistakes people make when they give the brief background information. They sometimes people have a 5-page proposal, 4 pages, 1.5 pages is about that software, what that software is doing. That's not a proposal, the proper one. Okay. If you have a 5-page proposal, at most 1 page is about that software. Probably should be half page instead of one whole page. Okay. So what this software is doing, and sometimes people go into history. This software was initially developed by some guy in Afghanistan, and then someone made this available on the web, and then now everybody is using it, and then people move this to the smartphones and other things. I don't need that much of that. Okay. Yeah.
So basically, for brief background, you just want to describe the functionality of the software you're testing.
Yeah, as it's relevant to your project. Yes.
If you decide on a technique at the time you submit the project proposal, and then you decide to, widely testing some of the data.
Yeah, that's fine. That's fine. Yeah, the only thing I ask you to do is to later on in your final project report, have a brief, very brief, maybe no more than a couple of lines discussion. This is the original proposal testing technique. Why it's not appropriate? Why you choose this one? Okay. So very brief, a couple of lines. Say your initial technique and your final technique. Okay. And yes.
For the final problem, like, how do you exactly define the problem? Is it like say test everything I can?
Well, you don't. Okay. Because this is a course project, and it's probably 1 or 2 person course project over a few weeks, and you cannot test everything you can. So you have to kind of decide what part you want to test, or what kind of subset of functions you want to test. Okay. Yeah. So if you or you want to say you want to just test to focus on what is important to you, evaluation strategy. Okay, so you'll say what's the scope you are testing, and what testing techniques you are using, and briefly say why do you think that technique is appropriate for this. Okay. And later on, when you find out it's not, then you need to justify why it's not, or why something else is better for this. Okay. And expected result, you probably not too much to say here, except that you was say, for example, that if it's a live project still going on, then you probably will be able to talk a little bit about what kind of result you expect and what kind of implications of those results and follow-up actions for those results. Okay, so for example, you are actively contributing to an open source development project. Then you found some things that thing about how to shaping the open source project or something like that. Okay, so we can talk a little bit about that. You have a question?
Yeah, means for the solution strategy, it will be the answer to the problem, which is in the
yeah, the solution strategy is more like kind of what other techniques you want to do. Okay, so you want to perform testing. What kind of testing you want to perform? Why do you want to perform that testing? And especially when you have multiple testing techniques, do you want to combine them? And combine them in what way? For example, I mentioned about some people say I want to highlight or look at customer usage, and then I can zoom in on some part, and I want to get some experience with the white box testing as well. That can be your solution strategy consisting of several different techniques.
the product should be having some problem.
Not necessarily. Yeah. The thing is that there's nothing is perfect, really. Okay. You can always find some problems, some kind of manner, but if you don't find any major problems, that's okay. That's not necessarily your fault. So that's okay. Yeah. But just don't kind of have the over expectation of something will be perfect. Yeah. You have a question? Yeah.
Can I get feedback on user interface, for example, of implementation?
Probably not as the focus of your project, okay, because this is the testing class. So user interface is a small part. You can do a little bit, but not that much. Okay. Yeah. Which will be more appropriate for the usability user interface design class. Yeah. Yes.
Do you like want to see that outputs and improve them in the testing? I mean, like to each job improve it.
You will be give some examples of those things, but then the main thing is that I will look at the collective result and analysis. So you see, one thing is that you will be executing probably not a couple of test cases. Maybe if it's appropriate for the class, and maybe you will be executing 50 test cases or so. Okay, and I don't expect that you write the details about each test case, but you should summarize what are the test cases, what they are, and what they do, and things. And if you want to, this is always something I suggest to people. If you think they should tell a good story, you can always include them in the appendix in the report. So the report, the text itself will be something about 15 pages, and then you may have some appendix. So in the past, I have seen quite a few project report more than 100 pages because they have a lot of things in the appendix. Okay. The individual test cases and test results, graphs, and sometimes they even include some code. Okay. No, I browsed through them, but I read the report. Yeah. Some. Yeah. So, the main thing is the report itself. And a rough schedule also. Okay. So when you will be doing what, and a rough schedule, and also if you are planning to make a presentation, let me know. Okay, in the proposal. And I really highly encourage people to give presentations. But if you really don't think you want to give a presentation, that's fine. But yeah, if you are planning to give a presentation, let me know, and also your preferred date of presentation. As I mentioned, I tried to reserve the last class or class after the week of Thanksgiving for distance students. Okay, and so for the on-campus students, you can choose now those 2 weeks before Thanksgiving. Any other questions about the project? So the proposal, what's the due date? I think it's about 2 weeks. So let me go back. Yeah, 22nd. Yeah. So, yeah, so it's which week is the 24th? Yeah, so it's 1 week from the homework due date. Yes.
So you said project report is going to be the same structure as.
Yeah. With more results. Yeah.
So could you how you expect to fill up like 15, 20 pages?
Well, say 15, 20 pages. Actually, people found that they need to cut and reduce instead of try to fill up. Okay. The thing that if you are doing a kind of project that is worthwhile to do for several weeks, then you will be using at least 2 testing techniques that are required, and many different test cases. Okay, so for example, let's say 50 test cases. Okay, and then you will have some description about the software and what it's doing, and then what part you are testing, and you choose this testing technique. Why do you choose this testing technique? That will be something like 4 or 5 pages. Okay, it's kind of like your proposal is about 4 or 5 pages, 3 or 5 pages. So that will be in your report, and then you use this technique. You construct a model. You need to show some of the important models, and then what does this model tell you? And then the test cases, a summary of the test cases in the report itself. Okay, how many test cases you have, what kind of test cases you have, and then the results. And then you need to analyze the results. I did this 50 test cases. I found 12 defects. Okay, and those 12 defects I found 11 from one testing technique, 1 from another testing technique. So in some sense, that's the kind of you can compare those 2 testing techniques as one is maybe more appropriate for this product, okay, and more effective in finding problems, okay, and how much time you spend on each of the things, so you can perform those kind of analysis. And also, with the result, there are actually 2 levels of analysis. One level of analysis is for the individual result. Okay, each of the things that's problem you found, you need to have some kind of analysis for that. Okay, so and then you can have an overall analysis. For example, I mentioned about you found 11 from technique A, find 1 from technique B, and you spend about the same amount of time, or maybe twice that amount of time on B, and find only 1/11 of the problem. Then you say, okay, the B is not really effective or not really applicable or suitable for this thing. And why do you think that's the case? Okay, and so you perform that analysis, and then you maybe talk about the follow-up actions, and so that will be easily 15 to 20 pages. Okay. And another thing that sometimes people this should be structured kind of like a technical paper. So with the report is more like a technical paper. So try to use different sections, and so that make it have more of a structure, not one long linear narrative. Okay. Have some sections and subsections if you least some sections. Okay. Any other questions about this? Yes. No, I don't give example project. Okay, but if you have some of the things, questions, we can always discuss more. Okay. Yeah, and I think I'm almost running out of time, and there is actually one of the homework questions talking about quality assurance, and software quality engineering. So I'll spend 4 or 5 minutes about that software quality engineering part. Okay, and so let me bring up the slides. So we have this one, and then so let me do a little bit of chapter 5, and okay. So essentially now we have this one. Okay. So we talked about the quality and quality assurance, but we didn't talk about quality engineering. Okay. And chapter 4 is really looking at the different activities and how they fit into the overall quality assurance from the kind of activity management view. We'll talk a little bit, spend a little bit time on that in the next class. Okay. But in terms of software quality engineering, essentially what we are looking at here is that now we do have the quality assurance. All the quality assurance that testing, inspection, formal verification, defect prevention, and fault tolerance, and those things. So those are particular quality assurance activities that we need to carry out. Okay. So software quality engineering is basically try to have something to get us prepared to do this, and have something to help us have monitoring and closure to do it successfully. Okay. So essentially we need to add 2 things to it. One is some kind of planning. Okay. So some kind of planning to help us planning for so that's some kind of quality planning. And another part is that while we are doing it, we need some monitoring and control. Okay, so that's the 2 new elements that added to become this software quality engineering process. Okay, so that is a new element, and then put them together. That's the software quality engineering process. When in the planning part, essentially there are 3 things you need to do. Okay, one thing, there are 3 things represented by the 3 outgoing links. The first one is that you need to set your overall quality goal. Okay, so you are doing as part of this product you are developing. This one, say for example, we mentioned this is a telecommunication product. The general expectation is that the downtime for over 1 year of continuous operation, the downtime cannot be more than a couple of hours. What you have there is a quality goal stated in terms of reliability of this product. Okay, and for other products, maybe you don't have that quality goal. Then you can say, okay, my quality goal is mean time to failure to this amount of no very severe problems. Okay, or if you have a number of problems, then on the average I can have maybe a few every month, but not hundreds. Okay, so you have some kind of quality goals that need to be set. Okay, and then of course when you set the quality goals, you have to consider your from whose perspective, what's the market condition, and all those things. Okay, so the quality goal will be used to control your quality assurance activities when you can finish the quality assurance activity and release the product. So that's the first part of the planning. Another part, now you set the goal. If this is a very high goal, very high bar, very high quality, then probably you need not just doing some inspection, you do need to do something like different types of testing, and you need to do fault tolerance and all that kind of things. Based on your quality goal, you need to come up with your quality assurance strategy, a mixture of different techniques and activities, okay, basically. Okay, and a selection of different techniques and activities, and how they get integrated, and how they combine, and how they are used together. Okay, so that's your QA activity, QA strategy. Then you need some monitoring strategy. Okay, so because you need to monitor the progress of it, okay, and to make sure that you are done. So you need some kind of monitor measurement models, and then your measurement and the models will be used as you go on with your quality assurance activities. And then say, for example, reliability is a goal. You need to collect data and say, what's the reliability now? What's the reliability if I continue with this for another month, for another half year? What's it going to do? So that you have your some kind of monitoring, and then based on your analysis, based on your data and the analysis result, you can decide to release the product. If it's ready, if it's not ready, to make some adjustments to your overall quality assurance activities. Okay, so that's the basic idea about you're not just performing those quality assurance activities in isolation, but then you need some planning, you need monitoring and control mechanisms. That's your software quality engineering process. Okay, so I'm running out of time, so that's it for now, and I will kind of quickly run through the rest of the chapter 4 and 5, and then 6 and 7. 4, 5, 6, 7, I will probably cover them all in the next class. Okay. Yeah. That's it for today, and good night, and see you next week, and don't